This is the Satellite Foundational course for JPSS on NUCAPS Soundings. I'm Scott Lindstrom from SIMS. What will you learn in this short module? I will define and describe NUCAPS soundings, explain how they're produced, and give a couple of examples on why you might find them useful. Many people have helped in the creation of NUCAPS. There are really too many to list here, but I thank them. NUCAPS is an acronym. Know a unique combined atmospheric processing system. It combines information from infrared and microwave sounders that fly on polar orbiting satellites to create vertical profiles of temperature and moisture. In 2025, those satellites are NOAA 20 and NOAA 21 from the US and Europe's MEDOPS-C. The instruments used are listed on the slides. There are infrared sounders and microwave sounders. When will you get data? Over CONUS in mid-afternoon and also early morning from NOAA 20 and NOAA 21. MEDOPS-C gives you information a couple hours earlier. Because NOAA 20 and NOAA 21 are both giving profiles, you get full CONUS coverage every 12 hours. As you move north, you get even more data. Here are sub-satellite points from one day. Of course, the data swaths associated with these sub-satellite points are much wider. The images on the top are around Hawaii. The images on the bottom are for the central part of CONUS. You see the times of the day when you have information from these different satellites. There's really quite a lot of it. The swaths tomorrow will be a little bit earlier and a little bit to the east of the swaths today. How long does it take for data to get into AWIPS, and what path does it take? There are two possibilities. Most of the National Weather Service gets NUCAPS from the SBN, the Satellite Broadcast Network, and the data will appear about 60 minutes after observations. Direct broadcast antennas allow for quicker dissemination of NUCAPS profiles. So places like Guam, Honolulu, Puerto Rico, and Alaska region, where there are direct broadcast antennas, can get the data within 30 minutes or so of the overpass. Vertical profiles are generated in a two-step method. First, a regression is run using static coefficients from 4 focus days that generated the best statistical fit between the observations and the vertical profiles on those days. These regressions use data from all infrared and microwave channels. This microwave and infrared regression is used to determine if the scene is clear or not. The retrieval uses a radiative transfer model to iterate to a solution that minimizes the observation minus calculation value. The calculation is the top of atmosphere radiance spectrum calculated within the radiative transfer model. The observation is the top of the atmosphere radiance spectrum. Initially, this is computed using the regression output. In regions of clouds where infrared retrievals typically fail, microwave data can still produce a retrieval. Microwave retrievals can fail where precipitation is falling. CRIS and EASI have many channels, and not all are used in the retrieval that creates the vertical profiles. There's a balance between adding information and adding computations. Two very close channels need not be included because they won't give independent information, but they'll still have to be processed. The channels chosen are those that are sensitive to only one gas, not to more than one. NUCAPS vertical profiles are usually smooth and typically have 6 to 10 layers of temperature information and 4 to 6 layers of moisture information in the troposphere. Don't expect to see very thin layers, hot or cold, dry or moist, in the NUCAPS vertical profile. They're very smooth. Fields of regard, that's FOR, from the CRIS are combined to create a NUCAPS sounding. The figure shows CRIS scans across a VIIRS scene. There are 30 footprints. A NUCAPS sounding represents information from a volume of air measured by up to 9 CRIS or 4 EASI fields of regard. Not a single point like a radiosonde. One field of regard that's cloudy isn't a problem, as long as there is a clear field of regard. Where do you find NUCAPS profiles in AWIPS? Look under the Satellite tab, then the JPS Polar, then NUCAPS Sounding Availability. That will give you the plot in the background with green, yellow, and red points. You can also access gridded NUCAPS fields in AWIPS. We'll talk about them in a bit. Gridded NUCAPS can also be found in the product browser under Grids, and then scroll way down to gridded NUCAPS. The color of the profile location, click on the dot and you'll see the profile, means something. Green means infrared plus microwave retrievals were successful. That is, the retrieval converged to a solution. Yellow usually means the infrared retrieval failed, but a microwave retrieval worked, and a microwave-only profile is present. Red means both retrievals have failed. Usually, yellow retrievals are where clouds are present, and red are where it's raining or snowing. The animation is showing you swaths over 8 hours. And I want you to take note of how much data there is. First, MEDUP moves across the country, and then the NOAA 20 and NOAA 21 do. Plot the soundings on satellite imagery so you can better anticipate where you'll have good and bad soundings. In this example, let's examine these 3 profiles. One in clear skies, it's a green dot. One near a cloud edge, also a green dot. And one in the cloud band where it's likely raining. The profiles are smooth. Note how the cloud edge profile shows a profile closer to saturation. A profile was created at the red dot, but do you think it's valid? It might show good values above the rain, for example the tropopause height, but that's not always the case. There are lots of soundings. If you select pop-up SKUTs in the volume browser, that's shown on the right, you can quickly scan through the field. This is useful to find gradients or thresholds that might interest you. After choosing pop-ups, right-click on the image and choose NUCAPS Soundings, and also turn on sampling. Now if you mouse over the sounding swath, a pop-up appears. You cannot change the size of the displayed SKUT, unfortunately. Maybe you're asking yourself, why not just use model output to estimate the current thermodynamic state of the atmosphere? Well, models can be wrong. Satellite observations are less likely to lead you astray. NUCAPS observations are most robust in the mid-troposphere. It's a challenge for satellites to penetrate through the atmosphere that is opaque to radiation at different wavelengths to get an accurate estimate of goings-on in the boundary layer, especially when the surface has variable emissivity as land usually does. NUCAPS does a little bit better job with this over the ocean, but you can adjust NUCAPS profiles in AWIPS to be more in line with surface observations. How do you manually adjust profiles in AWIPS? First, be aware of the surface observations. Click on a sounding to view it. If the surface values of the sounding are too different from the observations, this one is, you can edit it. Toggle Edit Graph to On. When you do that, points will appear on the sounding that you can drag to values that match what observations show. When you're satisfied, toggle Edit Graph back to Off. Now you have a profile that is more likely in line with reality. You can also enter Edit Data. This will bring up a text box that allows the user to change values directly at a level or to add levels. You can view horizontal grids from NUCAPS profiles. This example shows 500 millibar temperatures over a big data void. Multiple swaths from NOAA 20 and 21 allow users to see the thermodynamics over that region. Here's an example of NUCAPS use in a moderate risk from May of 2004. MEDUP-C profiles were created near 16Z, and NOAA 20 NUCAPS occurred around 19 UTC. You can use the profiles at the point to see how the atmosphere changed there in those 3 hours. You could also use gridded NUCAPS fields to identify horizontal gradients and how they might be moving or changing in strength. Here are the two profiles from the boot heel in Missouri. Perhaps the changes in these profiles can help inform your understanding of the atmosphere's evolution that day. Gridded NUCAPS fields show how values change over a large region. Here's an example of 850 millibar temperatures over the central part of the US. You see information from around 4Z and around 830 UTC. And here we see the multitude of data that are available over Alaska. Many swaths overlap, so you can track how things are changing in the short term. Note that gridding of NUCAPS fields uses data whether or not a particular profile converged to a solution. That is, it's using red, yellow, and green points. It's incumbent on a user to apply their meteorological good sense to screen out obvious errors that might arise from that. You could also put the NUCAPS sounding availability on top of this to see where the good profiles are. Here's a summary of what I've talked about. NUCAPS data gives useful thermodynamic information at least twice a day for all locations. It can supplement other data sources, radiosondes and aircraft, for example, to help you better understand the current state of the atmospheric thermodynamics. This concludes this short training. Thank you for listening.